Hi, in this video I'm going to teach you another method of factoring polynomials. This is one that we call quadratic in nature. Now what we mean by quadratic nature is that they factor almost exactly like a quadratic does. So as a refresher, a quadratic is a polynomial of degree 2. So you could look at something like this and it might be that that quadratic would be like x squared minus 13x plus 36. For that we know how to factor it. You can use the product sum. You find the two numbers that kind of match both those conditions, then you can factor it out. We call this quadratic in nature because it's going to use almost exactly the same process. If we have a trinomial, and we look and see the two variables, and we look at their exponents, and the leading one, is exponent 4, is double the middle one, 2, that tells us we can, or may be able to factor this like a quadratic. So we'll try this out with two different examples. All right, with the quadratic, we would do the product sum. So here, our product, our sum, and our numbers. Okay. See, the product, we take the coefficient of the first term, which is just a 1 here that's not written, and 36, so 1 times 36 is 36. We're looking for these numbers to sum to the middle term, negative 13. So now what I want to do is I want to find a pair of numbers that when I multiply them together I get 36, and when I add them together I get negative 13. So let's see, if I'm going to add them together at negative 13, I'm going to need two negative numbers. So I can start like negative 1 and negative 36. They would multiply to be 36, but they would not add to the middle there. Think through these things a little, and you end up coming with negative 4 and negative 9. It works because negative 4 times negative 9 is 36, and if I add negative 4 and negative 9, I get negative 13. Okay. Now the process will be very similar. I'm going to take this polynomial, it's degree 4, I'm going to split the middle term now into a negative 4 and a negative 9. So I get x to the 4th minus 4x squared minus 9x squared plus 36. All I've done here is I've taken this middle term, negative 13x squared, and split it into a negative 4x squared and negative 9x squared. Other than that, these two polynomials, these two expressions, are equivalent. From here, I'm going to group them together. X to the 4th minus 4x squared minus, now be mindful of negatives here, 9x squared minus 36. Right, the 9 squared becomes positive because I distribute the negative, it'd be minus. But if I distribute the minus to the minus 36, it'd become positive. Here, factor out the greatest common factor. X to the 4th minus 4x squared. The most that they share is x squared. So x squared times x squared would give me x to the 4th. And x squared times minus 4 would give me minus 4x squared. Subtracting, I can take a 9 out of both of these. Get 9, so I take a 9 out of 36, I'm left with minus 4. Right. At this point, I have the same binomial, so I can take that binomial out. X squared minus 4. So I'm removing those underlined terms now and factoring them out and looking to see what do I have left. And that would be x squared minus 9. Alright, at this point I have factored my degree 4 polynomial into two quadratic expressions, 2 degree 2. From here, you want to look to see if you can factor these quadratics. X squared minus 4 and x squared minus 9. Since it's a squared term minus a number, I can factor both of these. This one will factor into x plus 2 and x minus 2. X squared minus 9, likewise, will factor into x plus 3 and x minus 3. So when I completely factor out my degree 4 polynomial, I have it down into 4 different terms here. X plus 2 times x minus 2 times x plus 3 times x minus 3. And these polynomials are equivalent, they're just in different forms. Let's try example 2 here. X to the 4th minus 26x squared plus 25. Again, that's a trinomial, I look at the exponents and I have a 2 and a 4, so one is double the other. And this tells me that I may be able to factor this like quadratic in form. So product sum table. The product should be 1 times 25, which is 25. Their sum should be the middle term, negative 26. So thinking of numbers that could satisfy that, I know if I multiply them together positive and I add them together negative, they must both be negative. And negative 1 times negative 25 would be 25. Negative 1 plus negative 25 would be negative 26. So negative 1 and negative 25. From here, I'm going to split the middle term now. X to the fourth minus 1x squared minus 25x squared plus 25. Just splitting the middle term there. Next is be to group these together. So my first group minus my second group, being mindful of the negatives, so group together. Next thing here is going to be factor out the greatest common factor from both groups. First one is going to be just an x squared. The second one is just going to be 25. Take a look at this step. If the binomials are the same, that means that you've probably done things correctly, and further, that quadratic in nature will work for this. We have binomials the same, so I'll factor that out. Now I'm left with whatever is left in this expression after I take out x squared minus 1. Should be x squared minus 25. Okay. So this is the first factorization of my polynomial, and now let's look to see, can I factor any of the factors? These are both quadratics, and they both factor in the same pattern. X plus 1 times x minus 1, and then x plus 5, and x minus 5. Okay. So quadratic nature, to sum things up, is that some polynomials, even though they are much bigger, say x to the fourth, they actually factor almost exactly the same as quadratics do, which would be x squared. To do that, if we have a trinomial, if the exponents are double one another, we can try a product sum table, and if you can find two numbers that work, you can go ahead and split the middle term and factor just like quadratics. Once you get to this first level of factorization, you just have to make sure then that if you have two quadratic terms, see if you can factor either one of those. Other than this very last step, it's almost exactly the same as factoring quadratics.